Hello everyone. I welcome you to this class of econometric methods. Myself Dr. Muhammad Imdadul Haq, an associate professor at the Department of Economics, Aligarh Muslim University. Today we will be discussing Granger causality. See, in our initial classes we have discussed the difference between correlation, regression and causality. And see, in regression a variable depends on one or more variables, but it does not necessarily imply causation. And that existence of relation between variables does not prove causality. The idea of causality must come from the theory. But in time series, the situation is different. Now, Gary Coop suggested that time does not run backwards. So, if event A has happened before event B, then it is possible that A is causing B. However, it is not possible that B is causing A, as events in the past can cause events of today, but not future events. Means future events, they cannot cause events today. But events of the past, they can cause the events of today. So, this is in time series, the concept of causality is a bit different from basic econometrics. We can say that a variable xt is set is Granger causes yt if yt can be predicted with greater accuracy by using past values of xt than by not having such variables, all other things remaining the same. All other terms remaining the same. Say, in other words, xt is said to Granger cause yt if yt can be predicted with greater accuracy by using past values of xt than by not including the history of both xt and yt. So, this is how we talk about Granger causality. Now, if you go by empirical papers, you will find that they never write like x causes y. The terminology that is used is x Granger causes y or x causes y in the Granger sense. So, they want to make clear that when they are referring to this causality, it is they are talking about Granger causality. Let us consider our old var model, the same model y1t. y1t is a function of lagged values of x and lagged values of y. Similarly, xt is a function of lagged values of x and lagged values of y. And these two error terms are unrelated error terms. Now, there can be four cases over here. Case 1. Lagged values of x, that is xt as a group, is statistically different from 0 in equation 1. X is significant. Statistically different from 0 in equation 1. Lagged values of y as a group is statistically not different from 0 in equation 2. Here y is not significant. Statistically not different from 0. Statistically not different means it is, as such means we assume that it is equal to 0. In this case, it means y is not causing x, only thing is xt is causing yt, or we can say x causes y in Granger sense. So, this is the case over here. In the first equation, x is causing y, and from the second equation we see that y is not causing x. So, the direction of causality is one way, that is only xt is causing yt in the Granger sense in case 1. Let us go to the next one, case 2. In equation 2, lagged values of y is statistically different from 0, meaning thereby y is significant, statistically different from 0. And lagged values of x is statistically not different from 0. So, in this x is not significant. So, again there is causality running in only one direction, and that is y is causing x in the Granger sense. In the earlier case, x was Granger causing y, and in this case y is Granger causing x. So, case 2 we are done. Case 3. In equation 1, lagged values of x is statistically different from 0, means this is significant. So, here x is significant, and in equation 2, lagged values of y is statistically different from 0, means lagged values of y means here the coefficient. So, here y is significant. So, from the first equation we are saying x is causing y in Granger sense, and from the second equation we are saying y is causing x in Granger sense. So, both x and y are causing each other in the Granger sense. So, this is a case of bidirectional causality where x Granger causes y and y Granger causes x. In case 4, that is the last case, here x is not significant. Here in this, from the second equation, y is not significant. That is, the lagged values of xt is not significantly different from 0 in equation 1, and the lagged values of yt is not significantly different from 0 in equation 2. This means there is no causal relationship between x and y in the Granger sense. X does not Granger cause y, y does not Granger cause x, no causation. So, we have seen the 4 cases: x causes y first, second y causes x, third x causes y, y causes x, fourth x does not cause y, y does not cause x. In the steps of calculating this, we have we take this equation yt is equal to alpha plus summation of all beta j yt minus j plus summation of rj xt minus j plus e1t. What we do, we regress yt on the lagged values of yt alone. Do not include the lagged values of x. Now, this is what you are doing, you are putting restrictions. Here yt is regressed on lagged values of yt alone and this lagged values of xt are not included. So, we calculate RSS restricted. Next time we estimate the same equation, but we remove the restriction, that is, we include the lagged values of yt and the lagged values of xt. We calculate RSS unrestricted. So, we have the restricted RSS and unrestricted RSS. In the first case, in the restricted, we only we take the lagged values in this equation, we take the lagged values of yt only, and this was, if we take only these two, this is the restricted, and if we take this and also this was your unrestricted. Then we use the F statistics, so with the formula that restricted RSS minus unrestricted RSS divided by m. What is that is your m is the number of this will be m. This m is the number of lag terms in xt divided by RSS unrestricted. Divide this RSS unrestricted is divided by n minus k, where n is the sample size and k is the number of parameters in the unrestricted regression. So, if the restriction is valid, that is RSS restricted is greater than RSS unrestricted, we get a large F value, and if restrictions are valid, this means XT does not Granger cause YT. So, if RSS restricted is greater than RSS unrestricted, we have large F values. It means large F values means this will be, suppose this will be the table value decided by the critical point. We will get some values of the calculated value of F over here. So, if we are falling in this region, this is the region where we reject H naught, which implies, now this means that XT it Granger causes YT. We will repeat the same process for the next equation also. We will repeat the same process and we will decide accordingly. Now, one thing which has to be taken care over here is that Granger causality, it is done in the VAR framework. Now, therein the condition is that your data should be stationary. If it is not stationary, then we have to difference it and then we work on it. This was one of the issues with VAR. So, the same restriction is over here also. We can do Granger causality only if the data is stationary. This is being emphasized because Granger causality is also done in another case when there is co-integration and we are reparameterizing the model as vector error correction model. So, here also this one Granger causality you are doing in the VAR framework and one Granger causality we can also do in the case when the two series are co-integrated. If you remember that error correction term, that was say YT is equal to alpha 0 plus lambda ECT minus 1 plus this sigma, and you have this beta I delta XT minus 1 plus E1T. So, if this error correction term, now if we take this error correction term here, say I is equal to 1 and it extends to K. Now, this error correction, in this purview of error correction term also we can do, in this purview of vector error correction model also we can do this Granger causality. Now, if we can see that there are two conditions of causation, one is the lagged values of X and the other is the lagged values of the co-integrating vector. So, there can be, the causation could be because any of these two. So, this Granger along with Lin in 1995 said that the conventional Granger causality is not valid if two variables are not stationary, because two not stationary or integrated variables cannot cause each other unless there is co-integration. Meaning thereby this restriction is being implied over here, that you can do Granger causality only if there is an element of co-integration between the series. If there is no co-integration, then we cannot say that one of the series is causing the other, one of the variable is causing the other. So, if there is co-integration, we need to reparameterize VAR as VECM. So, here the coefficient and this lambda term of the ECT, the null hypothesis is all of them are 0, and if this null hypothesis is rejected if and only if these lambda coefficient are non-zero. In the conventional Granger causality, these terms are not there when we are doing it through the help of simply through the VAR. These terms are not there, this lambda is not there, these coefficients are not there, and this error correction term lambda is not there if we had not done co-integration prior to doing Granger causality. So, even if beta coefficient is equal to 0, but if lambda is not equal to 0, then H naught is rejected. So, what we do, we estimate the equation by OLS and then we obtain R square and again re-estimate by dropping lagged values of x and ECT and then obtain RSS square, RSS restricted, and then if test. Means once we have got the model in the var model has been reparameterized as VECM, then we adopt the same process which we are doing through the calculation of restricted and unrestricted regression sum of squares. So what we are doing, what exactly we are doing over here is this, repeating the same process, and here the variables are your x and the error correction term. So there are two possibilities what we have emphasized over here. One is we do Granger causality in the var framework, and another, if there is co-integration, then we can run VECM and then we do this Granger causality, or it is also called as block exogeneity test. Now we quickly see how it is done through the software. We have the three variables, they are entered into your eViews. We go to simply, we write all these variables together, x, y and z in the series. Then we say what are the lags to be included. We will decide upon that lags. This we are doing in the, this you can do directly. We go to quick and then directly you can go to Granger causality. So what we see, the first null hypothesis says x does not Granger cause y, and the probability is 0.38. The probability is more than 0.05. It means x does not Granger cause y. X does not Granger cause y. Now, next one is the null hypothesis is y does not Granger cause x. Now, here also the probability is more than 0.05. So, we can say at 5% level of confidence y does not Granger cause x. In fact, that is the same for all the cases. In none of the cases we will find that there is any element of causality between the variables. This we have done, we have gone to quick, and in the quick you will find the option of Granger causality, and we have directly done it. Now, we come to an interesting case which is done just similar to the process of Granger causality, but it is relatively new test. See, we know that let us go by some basics. If all the variables are stationary, we can do var or we can do OLS. If it is the case that one of the variable is stationary at first difference, the other variable is also stationary at first difference, then we do not do OLS, we go for Johansson co-integration. Also, one more model is there, that if one of the variable is integrated in first order while the other model is stationary, we go for, so it is not, the first series is I1 and the second series is not I1, rather it is I0. Then in this case we go for ARDL model, but there is a restriction, and that restriction says that none of these two, among these two or the other variables should be I2. If there is an I2, then we cannot estimate even using ARDL. Now, what if you have a variable, what if you have a situation wherein one of the variables is I2? In such a case, this Toda and Yamamoto test for causality helps us. So, this test is basically in the Granger causality framework. It was developed recently in 1995. What it basically does is it incorporates an extra lag. So, for doing this Toda and Yamamoto test, what we do, we first fit the var, and then we do a simple trick, and that is we augment with additional lagged values of the variables, and then in the third step we simply do the Granger causality test. And research papers, some of them like Wolde and Rufal and Ula and et al. These research papers have proved in their researches that this method does away with the restrictive conditions of stationarity and co-integration. We need not have co-integration among the series. We need not have the condition of stationarity. There can be mixed stationarity, and even a variable can be stationary at after second order differencing. If you just look at the values, if you want to specify it as a model, what we are doing, we are writing y in terms of lagged value. It is in terms of, if you just see at the model, yt is being written as alpha 1I yt minus 1, and then we take yt minus j, then xt minus 1, then xt minus j, then zt minus 1 and zt minus j. Similarly, x, xt minus 1, xt minus j, yt minus 1, yt minus j, zt minus 1, zt minus j. For z also we do it zt minus 1, zt minus j, yt minus 1, yt minus j, xt minus I and xt minus j. So, this is what we are doing. This is the basic representation of the model. More conveniently, what we do, we are just trying to show you quickly how it is done through eViews. So, what we do, we have estimated the lag length, and we take the lag length to be 1, then we go to standard var. Now, lag length was suggested, the suggested lag length is 1. There is lag length 5 is also, but we take the simplest one. So, we take lag 1, and if you see, we go for estimation of var, there we do a bit of trick. So, C is your constant. So, there was lag 1, so here we write the value of, we write y in bracket lag 2. So, we augment the lag, we give an extra lag. So, when x, the lag, although it was selected 1, but here we are writing in bracket minus 2. We again augment the lag for x. Similarly, we augment the lag for z. So, what we have done, we have augmented the lag. This is our output of the vector autoregressive estimation, although not of much use for us. Then what we do, we go to lag structure, we go to Granger causality test. Now we have a different result, and if you have a look at it, you will find that although in the case which we have discussed before, in this case none of the variables were significant, only one of them was significant at, you can say, 10%. Now in this case, this one variable, that is x is Granger causing y, it is significant just more than 5%. So, we can say it is significant at 10%. But apart from that, if you see, y is Granger causing z and it is significant at 5% level of significance. X is Granger causing z, and this one is also significant at 5% level of significance. So, with this we come to an end of our discussions on Granger causality and a related test of Toda-Yamamoto. So, we have seen that we can estimate relationships in terms of one variable causing the other differently in time series. And here we talk that that one variable can Granger cause the other variable. Here we have seen further that there can be 4 cases. If there, like in a bivariate case, x Granger causes y, y Granger causes x. In the first case is x Granger causes y, second case y Granger causes x, third case x Granger causes y, y Granger causes x, and fourth x does not Granger cause y, y does not Granger cause x. So, this was the 4 cases. we do the estimation by putting restrictions on the same equation of var which we have. While putting the restrictions, we calculate RSS restricted and RSS unrestricted, and we do F test, and based on that we take a decision whether there is this causality is there or not. But also there was one condition that for this the data, because it is being estimated in the var framework, so the data should be stationary, or if it is not stationary it should be differenced to stationary. But another concern was raised, and that was that if there is no co-integration, how you can say that two variables are Granger causing each other. So in that case, the var model, if there is co-integration, the var model is reparameterized as error correction model, and then here we again do the same F test of restricted and unrestricted RSS, and in this we use the independent variable or the explanatory variable and the lag term of explanatory variable and the lag term of the error correction term, and based on this the F ratio, again we take a decision whether there is a causal relationship or not. All the methods which have been discussed till now, that is Johansson co-integration or the ARDL method or this Granger causality, they have certain restrictions, like what should be the nature of the data in terms of stationarity. If there is a case where one of the variables is I2, or if there is a case that you do not find any co-integration between the variables, in such a case you cannot use the methods which we have named, like Johansson co-integration and also your Granger causality and ARDL method. In that case, where there is an other way out, that is we used Toda-Yamamoto test. Herein there is a simple trick that we estimate the lag, and then while estimating var we just augment the lag. Once we augment the lag, then again we go for estimation and we estimate the Granger causality, the same Granger causality which is done earlier. So once upon estimation we get the results for Toda and Yamamoto test. Hope this lecture was clear to you. Thank you.